the third quantum error correction session. Our first speaker is Chao Yin. He's going to be telling us about low-density parity-check codes as stable phases of quantum matter.
Thanks, and thank you all for coming.
This is joint work with Andrew Lucas at CU Boulder. So I have to basically tell you about the connection between error correction and phases of matter. So here I think I don't need to motivate why we need to care about error correction. For phases of matter, it is kind of a central theme in physics for us to understand quantum many-body systems. For example, if you want to study some materials like high-temperature superconductors, you want to draw these kind of phase diagrams, where although the system can have different microscopic realizations at different points, it is often sufficient to focus on the macroscopic properties of the system, which one would expect to be universal in the whole phase. So in other words, if you can show that some property holds for one point, then you can expect that while it is in the same phase, then you can kind of perturb it around so that you expect the property still is stable against the perturbations. And such stability turns out to be usually come from the error correction properties of the state. So let me demonstrate this connection with this canonical example of the Tori code. So we can define the Tori code by these two types of parity checks, either put a 4x's or z's, and you can just sum over them to get a Hamiltonian for the code, H0. And you can perturb your Hamiltonian by, say, an extensive sum of local fields and study the phase diagram. And you will find that, well, around this Tori code fixed point, there exists a kind of stable Tori code phase around it. And remarkably, this can be proven rigorously, first by this Bravi, Hastings, and Michailakis paper, which shows that, well, the Tori code is stable against any local perturbations as long as it has a small local norm, local strength, smaller than some constant, say 0.1. So here V is local if it consists of only terms that act on local regions. And the local norm is basically saying that, well, for 1 qubit, what's the total perturbation it feels. So this really justifies that this phase is actually a topologically ordered one, which goes beyond the conventional Landau paradigm in condensed matter. And the precise statement of this stability is that, well, when you look at the many-body spectrum of H0, you know that there are degenerate ground states or cold words, and there's a gap separating them with excited states. And basically, the gap cannot be closed when you add perturbations. And although the ground states can get splitted in energy, the splitting is exponentially small in the system size. Finally, there exists a quasi-local unitary U, or roughly speaking, a finite depth quantum circuit that can map from the old unperturbed ground states to the new ones. So in a nutshell, this tells you that the ground states of the perturbed Hamiltonian is still some very good approximate quantum error correction code. And later on, this has been generalized to show that actually any gapped frustration-free Hamiltonian in finite spatial dimensions with a condition called local topological order is stable against perturbations. So this is really a nice result for infinite dimensions, but we know that while codes in finite dimensions have fundamental limitations in terms of their code parameters. So that's why currently people are interested in this so-called quantum LDBC codes, where we can show that even asymptotically good codes exists, where not only the K, the number of logical qubits, but also the code distance D scale linearly with the system size. And so this is like the best code we can hope for. And for each such code, you define it by its X and Z checks, and you can just sum over them to obtain a many-body Hamiltonian H0. And because of this low density condition, this H0 is still some kind of local Hamiltonian on the bounded degree graph. So in some sense, this is still a kind of perfectly valid many-body Hamiltonian you can study in physics. So a natural question is to ask, well, do these H0s, are they stable against perturbations like the Tori code? Or in other words, do they represent kind of topologically ordered phases in infinite dimensions? And if so, then this will give you some kind of novel phases that actually violate the third law of thermodynamics And for more practical reasons, this is also related to whether you can use such codes for like self-correcting quantum memories. And this question has been considered in previous works, but with only partial results, because you can imagine that in this infinite dimensional setting, things can become really wild. And our work is basically saying that, well, to provide an affirmative answer to this question, know that similar results are also obtained in this independent work by de Roque and collaborators. In our work, we proved that a quantum LDPC code with a larger than log n codistance is stable against perturbations as long as it has this condition, which we call it checksoundness, which I'll turn to later. And the meaning of the stability is really roughly the same as the Tor code, which says that, well, the order 1 gap is stable, the energy splittings are exponentially small, and there exists a quasi-local entry U connecting the old and new ground states. In particular, this holds for all of the 3 known families of good QRDPC codes, and also for this hypergraph product expander codes, which, although strictly speaking, is not good, but it has much simpler constructions. So some implications, our results strongly suggest that these codes are stable self-correcting quantum memories in the sense that, well, we kind of prove that at 0 temperature, the system is in a stable topological-ordered phase. And in the next talk, you'll see that you can couple your Hamiltonian H0 to a finite temperature thermal bath, and it can retain quantum information in some exponentially long time. So by looking at this phase diagram, you will naturally kind of connect these two stability results to say there's an absolutely stable quantum memory phase. Since we show that these new ground states are still stabilizer states up to this easy to describe unitary, for experts from complexity theory, our results also show that, well, although such H0 may have some nice properties, which are called NLTS, you cannot just perturb them to get some Hamiltonian that will give you quantum PCP. Our results naturally generalize to classical LDPC codes. We prove that they are stable against symmetric perturbations, where the canonical example you can think about is the transverse field Ising model. And in finite dimensions, it is known previously that the Tor code is stable against spatially local perturbations, but here we can generalize it to even spatially non-local ones, as long as the perturbation is still field body. Finally, a kind of technical result is that we obtain a stronger locality bound on this unitary U, which is usually known as the quasi-adiabatic evolution. And this enables us to obtain certain non-local properties of gap ground states, which we derive in this later work. Okay, so I have to tell you how we prove our results. The high-level idea is to perform a high-order perturbation theory where we bound stuff in a rigorous way. So we start from this H0, which is a kind of block diagonal matrix where the 2 blocks are the ground states and excited states. And we perturb it, then H is no longer block diagonal. And the goal is just to find the unitary U that, again, block diagonalizes the new H. Of course, such a U always exists in this many-body hero space. But here, what we really want is a quasi-local unitary U, and that is often known as the Schrieffer transformation unitary. And we obtain such a U by an iterative process, where in the matrix form, you can view your original H as having some order ipsil, small off-block diagonal elements. And at the first step, you just want to find a quasi-local unitary U1 that just rotates the matrix such that its off-block diagonal elements become slightly smaller, becomes 1 order higher. Then you can try to find another U2 to further suppress it to ipsil cube, and so on. Note that in this process, you also update your diagonal elements. So if you write it as operators, then these diagonal updates are also included in this kind of D terms. So this is the procedure. And what we basically want to show is 2 things. So first, we want to show that this perturbation theory really converges up to a very large order m star, which is roughly the codistance. So that at that time, the off-diagonal part has become ipso to the m star, which is already exponentially small, so that we can just drop this term v star. Then we can just look at this kind of h star part, and by definition, we already know that it is block diagonal, but we still want to show that this h star is in some sense still a code, in the sense that these two blocks are separated by order 1 gap, and the ground state splittings are small. So this general proof structure is similar to the one used in the original BHM paper, but here we do need new techniques to tackle the infinite dimensional setting. And first is that, well, in this perturbation theory, we need to control the locality of operators. For example, we don't want, say, V2 to be immediately containing operators that act on the global system. And in finite dimensions, this is conventionally controlled by the so-called Lieber-Opson bounds. But here it turns out to be not sufficient, and we instead use this so-called cluster expansion type techniques. And at the very high level, the idea is that here we want to control the volume of an operator, where the volume being the number of qubits that an operator acts non-trivially on. So it's like Lieber-Opson bounds only controls the kind of diameter of the operator, and in this infinite dimensional setting, the volume and diameter can differ drastically between each other. Another technical stuff is this so-called check-soundness condition, which basically, we basically use that to show that this H star is still a code. So this will be the rest of this talk, is explaining what this means. So first, let us realize that the error correction condition or Neo-Lyapunov condition alone is not sufficient for stability, although it is in some sense necessary because you need that because that is equivalent to saying that the ground states are indistinguishable by local operators, so that when you add local perturbations, you indeed cannot split their energies. But perhaps for stability problems, the first thing you need to worry about is whether the gap can be closed by the perturbation. And it turns out that actually, for some models, very simple looking like perturbation V, which is sum over stabilizers, can already destroy the gap. So here, a stabilizer is a general element in the stabilizer group, which may not be the parity check of in H0. So to see this, let's consider this simple example, which I'll call it the icing toric code. So for the Euro toric code, it has these two types checks, AV and BP, being the X and Z's. And here, I still have AVs as the X checks, but I only have one particular BP naught with one plaquette P naught still being a check of this icing toric code, and all other BPs appear in nearest neighbor plaquette pairs, like an icing interaction. So you can convince yourself that this H0 has the same ground states as the original toric code, which is all AV and BP equal to +1. But this is unstable against such a perturbation, which is sum over BP. And what happens is that in the spectrum of H0, if you look at the subspace where AV equal to +1, but BP equal to -1, this is only a constant energy higher than the ground states. So when you add this BP, this excited states will immediately become the new ground states, so that the gap is actually closed already at order at an ipso, which is 1 over n. So basically, we want to avoid such pathological examples. And in finite dimensions, people have come up with this so-called local topological order as a sufficient condition for stability. So this LTO condition is defined, a model is defined to have LTO if, as long as when you look at any ball region with a radius smaller than codistance, I want all of the local, local ground states in S bar, being S plus its neighborhood, are indistinguishable by any operator in S. So formulate is in this equation where PS bar is the ground state projector of this local patch of Hamiltonian in S bar. And for example, when you take this S bar, instead of being S plus its neighborhood to the whole system, this recovers the error correction condition, so that you can indeed view this as a local version of error correction. And this also immediately rules out the icing Tarko example. For the stabilizer codes we consider here, LTO is equivalently stating that I want any stabilizer in O in S being expandable to a product of checks in S bar, so that I cannot use these stabilizers to distinguish the ground states in PS bar. So what we basically want to do is to kind of generalize this condition to infinite dimensions, and it turns out that you cannot do it in the most naive way. For example, it is not good enough to just consider the Ball regions in this bounded degree graph. And when you consider more general regions, the LTO condition does not hold in a straightforward way. So to tackle that, we need to consider some more algebraic generalizations of this condition. And that is what we arrived at, which we call checksoundness. So the code is defined to have checksoundness with the function f if each weight x stabilizer can be expanded as a product of smaller than f of x checks. So it's still about, well, I don't want a local stabilizer to have to be expanded as a product of many checks. For example, the Tar code, you can verify that it is checksound with f that is a quadratic function. Basically, you can always decompose a z loop as a product of checks that fill the loop. And for any LTO model in d dimensions, it will satisfy checksoundness with a polynomial function. On the other hand, the best checksoundness one can hope for LDPC codes is linear. And this is closely related to the condition called local testability in error correction, which is basically, like these two are basically both saying that, well, you want certain expansion properties when you do some mappings between bits and checks. So with that connection, we think that this checksoundness is a natural figure of merit to consider in LDPC codes. And in particular here, we prove that checksoundness with a sufficiently slowly growing f is sufficient for stability. More precisely, we prove stability as long as the code has a better than quadratic checksoundness. Or if you just focus on finite dimensional codes, then any polynomial would suffice. And it can be shown that all of the good QLDPC codes and this hypergraph product expander codes have the best possible linear checksoundness, so they are stable. So finally, let me provide some brief illustration on why this is a sufficient condition. So let's consider the simplest setting where I just consider V to be a sum over local stabilizers. Recall that this is already dangerous for the Eisenhower code. And this checksoundness is saying that, well, it exists a kind of one to a few mapping between V and H naught. So that when you look at any excited states in H naught, when you want to gain some amount of energy E or lower its energy, it has to always have a much larger energy penalty at the beginning from H naught, so that any excited states cannot be used to close the gap. So I guess I need to summarize. So there are certainly concrete further questions one can ask, but perhaps most importantly, I think our work and many other works have shown that, well, people have come up with these LDPC codes, and it is meaningful to consider them to ask their physics properties, which can bring you some very novel ones that you cannot get in finite dimensional cases. And maybe there are some more to come. And also maybe at some time we can reverse the direction to say that, well, after we gain sufficient physics intuition, we can use that to develop new codes or even classification theories of LDPC codes. With that, I will thank you for your attention, and I'm happy to take questions.
Thanks for the nice talk. And is it possible to define topological invariance for your system?
So I guess you can define it by the equivalence under local inter-circuits or local Hamiltonian evolution. So in that case, our theorem, like the stability here, belongs to that definition. Is that does that?
I'm asking for conventional symmetry breaking system can be detected by order parameter, and in 2D Tori code such as 2D topological order such as Tori code can be classified by their topological data such as modular data. And
I see.
it is possible to classify your system using some other mathematical object or something like that.
Yeah, I think that's a very interesting question. I think in general it's very unknown. Like how can you describe like anions in this kind of LDPC setting? I think that's a very interesting open question. Yeah.
Thank you.
Thanks for a nice talk. Physicists, like condensed matter physicists, often think of like phases of matter or states of matter. That's something that is defined in like a thermodynamic limit. And indeed, there's like theorems about phase transitions only existing in infinite dimensions and anything. So like, do you have a sense, presumably there's various finite size corrections here.
Mm-hmm.
Do you have a sense of like what they would look like and how important they are?
Yeah, so the corrections here are basically exponentially small in the system size or in the code distance more generally. So after that, everything is kind of perfect.
And do you think that's typical, or is there something special about these systems that makes the finite size corrections exponentially small?
I think that's probably typical for any like meaningful code that people would write down.
Okay, thank you.
Yeah, thanks for the interesting talk. I have a question on the point you mentioned a couple of times relating to self-correcting quantum memories. As far as I know, the statement is usually stated in terms of confinement properties of the syndrome.
Mm-hmm.
Is there a similar relation that you can make rigorous for the function f that gives the check soundness, or is it just a connection that you assume to be there?
So the check soundness is not directly related to the self-correcting quantum memory stuff, and I think in the next talk you'll see it was directly like the precise statement of confinement, which is not like this error of the function.
Okay, thank you. Then I'll just wait.
Hi, could you say a few words about the item about area law?
Yeah, thanks for the question. So I think in a nutshell here we prove a stronger locality bound for this U in the sense that the Hamiltonian that generates this U, it decays exponentially with the volume of the support in the operator. So it's kind of asking, well, can you really differentiate like diameter versus volume stuff? And I think like just modally that may be related to area law type problems. And more specifically, like these two problems are kind of related by this so-called filter function techniques, and maybe there are some more concrete things one can say along that direction.
I see. So what you mean is there's a hope of using this volume decay to do something about?
Yeah. We can discuss perhaps later.
I see. Thank you.
Hi. Thanks for the talk. I just want to follow up on the comment earlier on finite size scaling. So when you want to speak about like physics of matter, you want to do finite size scaling for like maybe 1D translational invariant system is easy because you can just elongate your chain.
Mm-hmm.
Whereas for LDPC codes, it's challenging to define a family of codes that scales like a service code. You just stretch it.
Mm-hmm.
So do you think this would have some implications on how to think about how to have family of LDPC codes that scale?
Yeah, I think that is not directly related to our work because we just prove for one particular code, and that is stable up to that e to the minus n error. And yeah, I can see that indeed for general code, maybe you don't know how to say append say one extra physical qubit to the code. I think that's in general maybe an open problem how to understand that.
Thank you.
I think we have time for maybe one more short question.
Thank you for the nice talk. I want to understand the check soundness in more detail. So, why such the check soundness is so important, and can you give any physical intuition of that? Is that check soundness physical interpretation?
Yeah, I guess perhaps the most physical way is to think about in the Tor code example, where I have this like stabilizers being the Z loops, and you cannot just expand this stabilizer as a product of checks kind of near the loop. You have to kind of fill the whole of it, so that, but it's still a polynomial checks on this, and that turns out to be sufficient for the split of the Tor code. And here we show that perhaps by this argument, it is also sufficient for general codes.
Okay, thank you.
All right, let's go ahead and thank the speaker again.